I'm going to go through one more example of finding the local extrema inflection points in concavity for a function. And this is the function. So let's start with the local extrema, which means I need to use the first derivative test, requiring me to find the critical points. So if you were to take the derivative using the quotient rule and simplifying, which you end up with for the first derivative is 1 minus x over 1 plus x cubed. And so to find the critical points, I will figure out when this derivative is 0 and when this derivative does not exist. Well, we can look here and see that the derivative will be 0 when x equals 1, and we can see that the derivative doesn't exist when x equals minus 1, but neither does the original function. So we don't count that as a critical point. The derivative has to not exist, but the function has to exist at that point. So I only get this one critical point of x equal 1, but x equal minus 1 is an important point. I'm going to put it down here, not as a critical point, but it has to still show up in my sign chart because it can change signs at that point. So I'm going to make my sign chart. I've got -1 and 1. And so I've got to put my factors over here. I'm going to have a 1 minus x, and I'm going to have a 1 plus x cubed. And so this one is 0 here. This one is 0 here. This is a linear factor and has a negative slope. So those kinds of lines will be positive, then they'll become 0, and then they'll dip below the axis, so they'll be negative. This is cubed, so it's going to behave like 1 plus x, but that's a line with a positive slope. Positive slopes, they're negative, then they become 0, and then become positive on the other side of 0. And so you can see if I hadn't included x equal minus 1, I would miss the sign change here. And that sign change matters because my derivative is negative, then it changes the derivative to positive, and then back to negative. So my function's decreasing, then increasing, decreasing. This looks like it's a local minimum, but since this isn't a critical point, this is the first derivative test does not apply to it. We can only apply the first derivative test to critical points. It is an important point, but it's not a critical point. And then x equal 1, we can see, is a local maximum. All right, that's all I get. It happens at 1. If I put 1 in here, I get 1. 1 plus 1 is 2, so 1/4. So it's a local maximum at that point. And then we go through the same process with the second derivative to determine the concavity. The second derivative ends up being 2 times x minus 2 divided by 1 plus x to the 4th. And so I'll create my sign chart for finding the inflection points. Let's find the potential inflection points first. Those occur where second derivative is 0 or where the second derivative does not exist. Second derivative is 0 when x is 2, and the second derivative does not exist when x equals minus 1, but just like before, the original function is not defined there, but x equal minus 1 is certainly a point we want to keep in mind because the graph, the signs could change at that point. So I set up my sign chart using -1 and 2. And I put my factors over here of 2 times x minus 2 and 1 plus x to the 4th. This is for the second derivative. This one is 0 here, this one is 0 here. So this one is linear with a positive slope, and those kinds of factors contribute a negative, become 0, then they're positive. This one's to the 4th power. Although it is 0 here, this is going to always be positive. So the overall result is negative, negative, positive. This is a change in concavity, so there's an inflection point occurring at 2. And when you plug 2 back into the original function, it's 2 over 3 squared, so that's 2/9. Okay, so that's what I've got for, and I didn't do my concavity. This is concave down, concave up. So that's what I get for concavity. And now I'll put it together, these two charts, and I'll try to get my graph. So start drawing a graph. Some important points are 1 1/4, 2 2/9. So I've got 1 1/4 and 2 2/9. So say this is 1 1/4 would be about here. So there's an important point. And then 2 2/9. Well, that's smaller than 1/4. So that's just a little bit below that one. 2/8 would be 1/4. And then I don't have any other points on my graph. I mean, I can always pick some more points and plug them in. For example, you can easily plug in 0 and see that that's going to give you 0. So, might as well get me a free point. There it is. The only other issue is this x equal -1. It kept showing up. That's not defined in the original function, but that's where I get a 0 in the denominator. And so what we know is that means x equal -1 is actually a vertical asymptote for this graph. So we'll need to keep that in mind. So here it is, -1's right here. This is 1 and 2, so I guess that's a little far, but anyway, we'll call it -1. So -1, we've got a vertical asymptote. Okay, so let's start drawing it. Let's start on this end where I've got all the stuff going on. It's got to be concave up from 2 on, and it's got to be decreasing from 1 on. So concave up and decreasing from 2 on. So, concave up, decreasing. This is concave down between here. From 1 to -1 to 2, it's concave down on that whole thing, which makes sense. It's got to come through here and it's got to approach this asymptote. So that part makes sense. So something like that, maybe. And then we'll come back to that. It's actually not right. We'll look at it. And then it's concave down up to -1. We've got the increasing, decreasing for the maximum, then it's decreasing up to -1. So it's concave down and decreasing down to -1. Well, that means it's doing something like that. And then out here, I don't know, something like that. All right, so that's my first guess at the graph, but we've missed some things. And what we've missed is the fact that this function, when I take the limit as x goes to infinity of f, this is a rational function, and we know that when the denominator has the biggest power, which the big power here is going to be x squared, this will go to 0, which means y equals 0 is a horizontal asymptote. So when I go back down here, I've got to put a horizontal asymptote in right here, which says, got a bit of a problem because for me to approach that horizontal asymptote, this thing's going to have to turn back around the way I've drawn it, and that would change the concavity again because it would become concave up instead of, it has to come back and become concave down to approach that, and it doesn't do that. This one can't approach it either because I've already passed it. It would have to change some concavity as well. So I didn't quite get this part right. Let me try to draw it over top. What should have happened over here is it comes through here like we've got, hits that maximum, changes concavity, but the reason it's changing concavity is because it needs to start approaching this. So it's changing so it can bend and approach that asymptote. I didn't do a real good job, but anyway, that's going to follow that blue dotted asymptote. And then same way over here, what's going to happen is it's never going to actually get up there. It's going to just stay down beneath here the whole time. If you go look at your function, you can see that the top, whenever I put in negative values, the top is negative, the bottom's always positive. So for negative values, this thing's going to stay below the axis. So the green graph is a better sketch of what's going on in this situation. It's got the concavity. I've also got two different types of asymptotes, vertical asymptotes and horizontal asymptotes. And here's the actual graph, and you can see I've kind of caught it. It's hard to see the concavity change here because, again, it's subtle. But the farther out I go, it'll have to keep bending to follow that graph. So there is a bit of a concavity change, even though it's not that recognizable when you actually look at a graph.